The next topic or lecture is lecture 13 on transformation geometry, and transformation geometry is new, so therefore you'll have to familiarize yourself with it, but you've done it in grade 9. The word we need to look at some concepts which are very important. Symmetry firstly. The word symmetry is synonymous with the words such as balance and proportionality. There are two types of symmetry. Reflection symmetry. Now the design can be folded along a line of symmetry, so that all the points on one side of the fold exactly coincide with the corresponding points on the other side of the fold. The rotational symmetry, the design is a rotational symmetry if it can be traced and rotated less than 360 degrees about a point, so that the tracing can be made to fit exactly onto the original. And when we looking at the concept of transformation geometry, it's very simply put, this is geometry in motion. The movement of all points of a geometric figure according to a set of rules creates new geometric figures. The new figure is called the image of the original. If each point of the image can be paired exactly with one point of the original figure, then the correspondence is a transformation. A transformation that preserves the shape and size as well is called a rigid transformation or isometry. According to Greek, the Greek meaning is same measure. The image is congruent to the original. Now there are three types of rigid transformations. That is the translation, which is a slide, the rotation, which is a turn, and it's like, when you're looking at the hands of the watch, analog watch, and then reflection, which is a flip. The Cartesian coordinates. Transformational geometry, we're looking at translation in the Cartesian plane. Now this is what we're going to focus on, and the ratios between distances. And then rotation, we're looking at angle measures, and when we do enlargement or dilation, ratio and percentage, and then reflection about the Cartesian axis. Notation for an image: if A is the original figure, then the image of A is A prime. Let us look at some practical cases of transformation geometry. When you look here, let's look at the figure 1, and I've got it in 4 quadrants, and let's take A, B, C, D, which is P. That's the original figure. Now if you look at A prime, B prime, C prime, D prime, or P prime, it is a reflection. It is the image of A, B, C, D, and you will find that if we say it is a reflection of A, B, C, D, then we are actually looking at, you will notice that B has actually flipped its position, and D also, because D remains. Now one of the central things about what are the coordinates of P prime, they said. So if you look at the coordinates of P prime, now it's very simply the case of actually going up there, and then because that will act as the y-axis will act as the axis of symmetry, and that's it is a perpendicular bisector. So A prime is the image. So if we take this now to be the exact distance, even if you use your if you use your x is 0, y is 6. So if you say 0 is equal to minus 3 plus what will give you minus 3 plus what will give you the 0. So you will get x is equal to 3, and then you will get the 6. So that is the mirror image. That is why we say it acts like a mirror. Now you can work out all the other coordinates. It's not very serious, using the same principle that I spoke about. You must know the line of symmetry for that. So what is the line of symmetry of P and P prime? It's the y-axis. Now you will notice that the coordinates are related. It's your x value. It's only the signs that have changed. The sign that has changed. Now if we take the second case, and the second case here is P double prime. Now if you take P to be the original, then how could we move to P double prime? Now there is a rule that's given here now, and they say x plus 7. X plus 7 means you got to move the entire figure 7 units to the right, and 7 unit, and y minus 7 means 7 units down. So if you know the coordinates of let's say, which are minus 3, 6, then A double prime will be minus 3 plus 7, which is 4 as the x value, and the y value is 6 plus minus 7, which is minus 1, and that's perfect. So that is actually a translation. And then we move on to P triple prime. P triple prime, which is the image of P. P, let's say, which is, if it's the image of P, then it means it's flipped about the x-axis. So it could be used, it could be reflection. Or if we take from P prime and we had to move it to P triple prime, now this is actually a rotation. Now a rotation, now the rotation is about the origin, because that is a restriction that is placed on the curriculum, that the rotation is about the origin. Sorry about that. And if it's about the origin, then it means you're now rotating it, and we're rotating it anti-clockwise, and let's assume it's rotated 180 degrees anti-clockwise, then it will reach, then you'll get these points, and then you can work out the coordinates of the points for the rotation. Lecture 13 is from page 55 to 62, and we're now looking at a particular problem, which is 2.1. Now what is very, very important about these problems here is that if you do what we're doing, we're going to do a reflection from first principles, we're going to do a rotation from first principles, and then we'll do translation as well. So let's do the first one, which is reflection of A about y is equal to x. So this line here is y is equal to x, and we have this point A, and A is what we have. A is 4, 1. And now I want to reflect it about that line. So I did say that we're looking at the mirror image, and this will become A prime. So the question is, what are the coordinates of it? So we know they equal there, and this is your perpendicular. Now from first principle straight away, what we need to do is to find, if I can find this point here, which we will call M as our midpoint, then I can find the coordinates of A prime. Now what we are looking at now, we need the gradient of this line, and because they are perpendicular, the gradient of, let us call this line here L1. So the gradient of L1 is 1, and the gradient of AA prime, is equal to minus 1. And then we got your equation y minus y1, y minus 1 is equal to minus 1 into x minus 4. And then you'll get y is equal to minus x plus 5. Now, we've got that, and we've got y is equal to x. Solving these two equations simultaneously to get m, so you will notice now, if we add these two, we'll get 2y is equal to 5, y is equal to 5 over 2. And your x, y is equal to x, so the x is also equal to, x is also 5 over 2. So your coordinates of m are 5 over 2 and 5 over 2. So if we look at now, taking this further, one step further, so it's straightforward. 5 over 2 is equal, let's call this point A and B. So 5 over 2 is equal to A plus 4 all over 2. So A plus 4 is equal to 5, A is equal to 1. And then if you look at the next one, 5 over 2 is equal to B plus 1 all over 2. So then you will say that B is equal to 4. Therefore your coordinates of A prime are 1 and 4. Now, and you notice that if you're reflecting about the line y is equal to x, then you interchange your x and y. It is also contained in the booklet. Now they wanted you to reflect this image about y is equal to minus x. Now I'm certain that I could actually leave that to you to reflect this. What you're basically looking at is, if you look at this diagram here, you have 1, 4 there as A prime, 1, 4, and what you want to do is to reflect that about y is equal to minus x. That's what they wanted you to do next. And using the same principles, you can reflect it. Don't worry about which quadrant it is showing. So that will be A prime, this will become A double prime. And then using the same principles, you can work that out and see what it gives you. This problem here is number 3. Now it says that R minus 2, 6 is the reflection of R prime. Now about the line y is equal to mx plus c. So if we do this and we plot the points R, which is minus 2, 6, and then we plot the point R prime, 2 minus 2, and then you will get, now it says it's a reflection. So what does it mean? That it means that you're given that we need to know what was it reflected, what is the axis of symmetry in respect of this. Y is equal to mx plus c. So if we take this now and we look at and we go back to what we would normally look at, let's find the coordinates of m, which is the midpoint. So the coordinates of m is minus 2 plus 2 divided by 2 is 0. 6 plus minus 2 is 4 divided by 2 is 2. So we've got that as 0, 2. So all we need is a gradient. And we can get the gradient from this one here. So the gradient of r prime is equal to 6 minus 2 is 6 plus 2 is 8 over minus 4, which is minus 2. And the gradient of this line here, which we can call L1, so the gradient of this line here will be change the sign and invert, which will be off. So the equation is y minus 2, that's the m coordinates, into half into x minus 0, and you've got 2y minus 4 is equal to 2y minus 4 is equal to x. So we can leave it as y is equal to 2y is equal to x plus 4, which is fine. And then they wanted you to write it as y, m and c. The one they will give you find m plus c. So m is a coefficient, which m is 1, and then your c is 4. And if they ask you to add those two, it will give you 5. This problem here is on translation. It's on page 58, and it is number 2. And they also want you to, well, we said show the translation, because obviously you're learning this section here as well. So let's just quickly look at this graph, and then we get a better idea of what's happening. Now you'll notice that this graph here is y is equal to x squared, which is a parabola. And according to this, they want you to move this graph 3 units to the right. Now if I move it, it's 0. If I move it there, this graph should look like that's what's going to happen. So this coordinates here is 0, 0. You'll notice it's moved now 3 units to the right, it becomes 3, 0. Now the question is, what is this equation and what is the easy way to do it? Now I always suggest to people is to say, I've got the 3 here. If I replace the x by 3 in the original, I'll get a point here 9. 9's, x is equal to 3, 9. And then on the other side, I've got minus 3, 9 as well, which is quite interesting as well. And now, how do we get this equation out here? And many of you have seen that if you just take it, we do an ordinary substitution, you're going to have problems. So there is your translation, I've shown it. So if I say x plus 3 here, and make it x plus 3 all squared, I'm going to end up with a problematic result. So in other words, if I did this, x plus 3 all squared, and since there's no movement of y, we don't have to worry. Now that is obviously going to be x squared plus 6x plus 9, and the excess of symmetry here is minus b over 2a, so it's minus 3. It's on that side. So therefore, now you'll notice that as a result of this excess of symmetry, it is x minus 3 all squared will actually move the graph 3 units to the right. So please keep this in mind for the value of x. As far as y is concerned, it doesn't really matter. Now if you took the one where it said in number 3, actually it said they wanted a translation to be done for the same problem, x plus 3 and y minus 2. So this translation here would have been, if we look at both now, it would have been y is equal to x minus 3 all squared, and I want you to move this graph 2 units down. So if I move it 2 units down, it's got to be a minus 2. Now, and if you try to do that, then you will see you got a 3 and a minus 2, because you remember what we did say previously, y is equal to a into x minus p all squared plus q. That is your axis of symmetry, and that's your maximum or minimum value. Coordinates of a turning point. So that will become, the turning point will now become 3 and minus 2. Now you have sufficient problems there, but I've given you also the fundamental ideas about translation, and you can get these translations in your National Senior Certificate exams as well. And I've given you rotation. I've done the most difficult problem there, and I've taken you to reflection from first principles, and that concludes this topic on transformation.